The HDMI.
This is not required.
Can I test?
Yeah.
This thing. Okay. Readable enough. There we go.
Welcome back. Now I would like to invite Anshul Singhvi, contributor to the Makey.jl data visualization library and the author of its geospatial extension geomakey.jl, also an author of the geometryops.jl package for 2D geographic geometry processing and contributor to many other packages in JuliaEO ecosystem, interested in geospatial problems and how principles from other fields can be applied to solve them. Anshul.
Thank you. Hey everyone, so, oh boy, my laptop is almost too wide to fit there. Yeah, so today's presentation is mainly going to be just an update on what's happened in the JuliaEO ecosystem over the last year. So before I start, could I maybe get a show of hands of like how many people are familiar with JuliaEO or have used a JuliaEO package before? All right, cool. Okay, so not too many folks, so I might, I'll give a quick intro of the ecosystem and what it has. But yeah, so JuliaEO is sort of this umbrella organization for geospatial infrastructure in Julia. So it's got, you know, I/O packages, geometry processing, raster processing. So raster is just gridded data like satellite images or things like that. And the sort of goal of this organization is that the whole ecosystem should be intercompatible, composable. You should be able to take a data structure from one package and put it in another package in a context that makes sense, and it should just work. Right, so here's some notable packages, and I'll go over a bunch of those later. But we have GeoInterface, geometry ops, and rasters, which are sort of the quote-unquote flagship packages along with geodata frames. You have some I/O packages here. You have some visualization stuff. You have some wrappers of C libraries, right? So it really has a bunch of different things. So it started out as a collection of I/O tools, right? So you had a wrapper of GDAL. You had native Julia stuff for shapefiles, netcdf, so on. Then it branched out into wrapping more stuff. So libgeos, which is the current sort of industry standard 2D geometry library, proj for projections, you know, so from the sphere to the plane and so forth. And then started having some pure Julia algorithms. So geodesy was arguably one of the first ones. Also more coordinate transformation, but yeah, so now it's an ecosystem of these interoperable packages. There's lots of I/O. So most vector geometry formats, your GeoJSON, your shapefile, a bunch of other things, GeoArrow, for instance. You can do I/O on all of those. Of course, we also have I/O for raster data, so netcdf, ZAR, a bunch of other things like that. Raster processing tools in rasters.jl, which is things like zonal statistics or resampling your raster data and things like that. and visualization tools. So Tyler is for map tiles, so sort of your Google Maps kind of experience. Geomarchy is more for managing projections. And so if you have data in one coordinate system, you want to plot it in another coordinate system, that's how you do that. And these are all tied together by this package called geointerface.jl. Now, I'm going to switch to my set of slides from last year. Just to show, so geointerface is this common interface that defines how you access the contents of a geometry, right? So a lot of other ecosystems don't really have this issue because they have one canonical form for what your geometry is supposed to look like, right? Like, let's say a polygon is, a vector of vectors of points, right? They'll say, okay, this is the only way that I will understand a polygon is if it's this particular structure, which is, a vector of vectors of length 2, right, which are your points. In Julia, we don't necessarily do that. Or in JuliaEO specifically, right, we allow you to have any sort of memory layout that you want, right? So any structure that you want, so long as it implements this interface, so this set of functions. And so this allows multiple and pretty different representations of geometry to coexist in the same ecosystem. So let's say that your use case is one where you really want all of your x coordinates in one array and all of your y coordinates in another array for each geometry, right? You could do that. And with this interface, that would be perfectly doable. Whereas if you want to, for example, you want to read GeoJSON, right? So you want a structure that exactly mimics what the JSON looks like. You can do that too. And in fact, we have done that, right? So that's sort of the point. Let me see. There's, of course, plotting support as well, right? So any geometry that you have, you can just call plot, either from plots.jl or marquee.jl, and that just works. So yeah, that's sort of the very short ecosystem primer. So last year, right, because I gave a very similar talk at JuliaEO in 2025, intro to the ecosystem, we talked about formalizing the interface for vector I/O. We talked about consolidating things under geodata frames. Both of those got done in the course of this year. So I don't know if Martin is here, but thanks, Martin. Martin is the developer of geodata frames, which he's talking about that on Friday. We actually hacked up the first implementation of vector data cubes, which is basically n-dimensional arrays where one or more of the axes of the array represent some vector data. So one of the axes may be polygons of countries, or it may be points where you've sampled something, or so on. Unfortunately, that's still in a PR, but it's a much better PR. So I'm hoping that this year we get that. We also formalized a governance structure, so I'll talk a bit more about that, but this was sort of inspired by a conference we went to that also decided to form a similar governance structure this year, and basically the idea is we just have a steering committee which is enabled to break deadlocks and take decisions that otherwise would just never get taken. And lots of other package improvements, of course. So looking ahead, well, I'm not going to say a timeline, but medium term, right? We want to overhaul the JuliaEO new user experience, so the website, the tutorials, references, user guides. We have a book. We were translating a book which is quite popular in the Python and R ecosystems to Julia as well, so ideally we get that done. And yeah, a bunch of other PRs, a convenience package so you don't have to use these so right now, if you look at this list of packages, you would basically have to say using every single one of these packages in order to get all of that functionality. So we have a concept going which would make it so that you don't have to know exactly which packages you need. You just have to use this one package and it loads everything for you. And then there's also been quite some work that started off last year and hopefully will finish in this conference, or at least we'll get a working version in this conference, of regridding from sort of a latitude-longitude data set to something to a spherical representation of that. So if you've heard of HealPix or IC or things like that, and I'll show some examples of that later. But yeah, so governance. So we now have a steering committee in JuliaEO, of which I think 1, 2, 3, 4, 5. 5 members of that steering committee are in this room. And so we've currently, I think, got 8 people in the steering committee. it's mostly empowered to resolve both technical questions and deadlocks in terms of like, oh, I think this is the right way, but this other person thinks this is the right way. All right, let's get in a room. We'll have the steering committee there. Everyone presents their piece, and then we say, okay, let's do this or let's do that, right? Or some compromise. And also organizational and social questions. So there are a couple of those. Ideally, we probably meet once a quarter or so if necessary, but it's not a super huge time commitment. There's also been semi-regular monthly community meetings. I really need to find someone else to help run those. But those are also very nice just to keep a sense of community and sort of progress going. Next thing on the list for us as a community is to figure out a mission statement and then overhaul our website to reflect the sort of new state of the ecosystem. There's also been a bunch of conferences with JuliaEO participation. So, of course, same time last year, JuliaCon in Pittsburgh this year, ESA's Living Planet Symposium, the Spatial Data Science Across Languages Conference, which if any of you guys are interested in sort of spatial data science more broadly, that's a very interesting conference to go to. Basically, it's developers of packages in R, Python, Rust, I think some people in the JavaScript world as well. All of these guys come together and just discuss questions about sort of how you interpret geospatial data, what's the correct way to handle certain things, how should we make sure that packages can interoperate and so on. So it's pretty interesting. Big Data from Space, which was in, I think, October in Riga this year. JuliaCon Paris, and of course this conference. There'll be a bunch more next year. So yeah, if any of you happen to be at those conferences and we happen to be there, do say hi. Yeah, so before I start talking about updates, I'm going to give a brief walkthrough of how this whole ecosystem actually works, right? Okay, so is this big enough for everyone to read? Perfect. So let's say we're downloading some kind of vector file, right? This is a GeoJSON, and this is all of the countries in the world. So as this downloads, sorry, this is fresh Julia session, so it takes a while. So you can see that this is a regular GeoJSON file, right? It's got a bunch of metadata in it, and then as you scroll down, it's got these coordinates, and you define the type of the geometry. So okay, we can say using geodata frames, and then read the vector file in by geodataframes.read. Right, and you just pass the file name there. File name is just a string. And what this gets you is a Julia data frame object, right? It's got a column called geometry, and it's got one column for every other element of metadata that you have in your feature collection, right? So this is specifically for reading in vector geometry. There are other ways to read in other kinds of data. I'll get to that in a bit. So let's see, what can you do with this? Well, you can get, it's a regular Julia data frame, right? So anything you can do with the Julia data frame, you could do here. One of the first things you can do is you can say, okay, I want to get, the first element of the geometry column, or I want to get, oh dear. I want to get the name of the first country, right? It happens to be Indonesia. You can also plot. So I'm going to use Kairomaki here. And we've got, plot. This is, so one interesting thing here is you're actually plotting the geometry vector and you're passing the color as another vector, right? So it's not necessary. There are other ways to do table-based plotting in Julia. Algebra of graphics.jl and Maki is one of them. But for now, I just decided to showcase the simple way. Right, so this is a pretty simple plot, latitude, longitude. You've got polygons colored by some value, right? And that value can be anything. I mean, I can make this right, so I can give it random RGB values, and that also works. So it's pretty flexible. And oh yeah, by the way, please hold on. I'll send the script. I'll upload the script to the repo, the JuliaEO 26 repo, once we're done here. But yeah, please feel free to stop me and ask questions if anything is particularly confusing. Yeah, okay, so we've shown sort of how you load data, how you plot data, right? Now, getting into this geo-interface thing. So I'm going to import the package, geo-interface, and I'm going to select one geometry that I want to really look at. So first of all, the question arises, what is this geometry? So that's a good question. Geo-interface has this thing called a trait. And so any geometry has to have a certain trait, which is the sort of kind of geometry it is, right? So this could be a multi-polygon, a point, a line string, that kind of thing. I can also get the extent, which is just the bounding box in latitude, longitude. I can get the coordinate system that this is in. In this case, this is just standard latitude, longitude, as you can see here. And then I can also get the number of geometries within this one. So there's 264 polygons in this multi-polygon. And I can, let's say I get the first geometry, right? So G1 is this, and then I can of course keep going. Right, so that's a polygon. Its child is a linear ring. And then its child is just a point. So that's sort of the way the hierarchy sort of unfolds. Then, of course, you can do things to these geometries. They would be very uninteresting if you couldn't. This is where this geometry-ops.gel comes in, right? So geometry-ops is a package for performing many kinds of operations on vector geometry. So let's do something very simple. I can get the perimeter of this geometry. I can get its area. Those numbers seem kind of low. This is Indonesia, right? It's got a very large population. I don't think they're living on 495 square meters. So why is this wrong? This is wrong because we're computing the area in latitude-longitude space. So we're saying, okay, this is a polygon. Its first point is at latitude 71, longitude -4 or something like that, right? But you actually need to treat it as if they are points on a sphere. And so I can say, okay, get me the perimeter, assuming I'm on a sphere. And this seems broadly more reasonable, right? This is like 4.31 times 10 to the 12 meters squared. And if I Google this, oh, that's a bit odd. I must have a bug somewhere. Okay, yeah, I have a bug in my implementation. So I swapped out the backend for a different backend. So in Geometry Ops, you can basically select whether you want to compute on the plane, the sphere, or the ellipsoid, right? And you can also specify which ellipsoid. So the default one is actually planar, right? And so that just gives you the default implementation, which is default interpretation, which is on a plane. Then you have an interpretation on the sphere, and geodesic actually calls out to a C library that does this computation. So there's really a bunch of different, and this is just specifying what I ended up calling the manifold, for lack of a better term, right? Which is the sort of space that your geometry lives on. But you can also specify different algorithms as to how you compute a particular thing, which becomes quite useful. So yeah, okay, so I did not realize that this was that buggy, but you always have options. And so now this is not, of course, not all you can do with it. Let's take 2 polygons. So let's see. I'm going to find the US, or not, maybe not the US. Let's see. No, Portugal also has islands. I'll find Switzerland. Right, so I'm just going to find the first element in countries.name, that is Switzerland. Then I'm going to say, right, so I get that geometry out. And I can also transform arbitrary geometries using geometry ops. And in this case, I'm going to get its centroid first, so Switzerland. Right, so this is the longitude first, latitude second, which is the geometric centroid of Switzerland. And then I'm going to just flip that along flip that about its center along the y-axis. So let's see. So I'm going to do a pointwise transformation, right? So this becomes, let's see, so this is a point. So I will return, let's see, negative x minus AI autocorrect. Right, so basically what this is doing is I'm passing this geometry into this function. This function is going to decompose it down to the level of each point. And to each point, it's going to apply this function inside and then reconstruct the geometry. So this doesn't just apply to a single geometry. You can also apply this to the data frame that we had, which is the data frame called countries, right? You can apply it to a bunch of different, you can apply it to a vector of geometries, you can apply it to basically any data structure. So let's plot these. Put this over here. Okay, so you can see these kind of overlap. Now we can take the intersection of the two of these. And the UX is still a little bit annoying right now, which we're kind of working on, but you have to specify what kind of output type you want. And that's mostly for type stability on the Julia side, but like I said, sort of working on that. So you'll notice that this output looks very different from the input. So if I look at Switzerland in the REPL, I get something that looks like this. And if I look at the type is this thing, right? Now the type of the output of this, which is this quite complicated thing. And this is sort of the cool thing about GeoInterface is that as long as whatever you write sort of quote-unquote obeys the GeoInterface, right? It only uses GeoInterface functions. It doesn't depend on specific aspects of the type that you're working on. Okay, I have a little bit of time. As long as you only work on the GeoInterface API, it doesn't matter what the input type is, and you can construct whatever output type you want. They'll all work in the same functions. So I can also plot, of course, I can also plot this. And that looks like the intersection area. So yeah, that's sort of most of geometry ops in a nutshell. There's also a bunch of other cool stuff. Documentation still needs work, but it's getting there. So that was vector geometry processing, right? And the other thing that you should also know is that you can also check whether two things intersect. So you can just use intersects instead of intersection, right? And that of course returns true. But if I look at Indonesia, of course they don't intersect. Okay, so that's vector stuff. Let's look at raster data for a second. So raster data is usually data that exists on a grid, right? So that could be data from a simulation, right? That could be data from a satellite image or processed products from satellites. Could be a lot of other stuff. But for now, let's see. So rasters.jl is the package that lets you do this. And let's see, what kind of data would we want? So I'm going to use a package called raster data sources. Oh, wait, no. Let me find a I have to find something. So Natural Earth is a website that has a bunch of interesting geospatial data. Let's see, medium scale, raster. Yeah, all right, let's see. I guess that's not really meaningful though. Okay, I'll use a package called raster data sources, which basically, it's a Julia API that allows you to get a bunch of different sort of predefined data sources for a raster. And so let's see, at this point, let's see if I have this in my project. I have to add that, so while that's working, I'll type it out. So I'll have to, I don't exactly remember what this was, so I'll get this code from another example that I was running, which happens to be here. Okay. Okay, so this has given us, print this out again so you can see. So this has given us this data type which is called a raster, right? This is also a Julia array. Its element type is it's got missings and U and 16s. It's a two-dimensional array, right? So it's a matrix. But then it's also got these dimensions in it. So it's got this X dimension, which is, of course, your longitude, Y dimension, which is your latitude, right? And it has some metadata. So let's plot this. Right, so in this case, this is, I think, I'm not entirely sure what this is. I got it like a couple of hours ago. I should really remember. But yeah, so you've got this sort of thing, right? You can see that it's data over land. Probably a couple of very, very high outliers. And so what can you do with it? Well, of course, you can index into it, right? So you can get the raster at some index within it. But you can also index using sort of logical qualifiers. So let's say it probably has something in the Azores. So let's check my current latitude and longitude. Okay. Yeah, that seems correct. Okay. So I'm going to index using, so I'll say I want the raster at an X position near the longitude value and a Y position near the latitude value. Oops. So that also gave me a missing, which is, I guess it doesn't have information on Terceira. But yeah, so basically you could change this up to, okay, let's get, oh gosh. 50 comma negative 110. So 50, up 50. This is negative 110. Right, and this gave me some value. And let's see. So I want to get something a bit more meaningful here. It's word climb climate. So this will download on demand as well. But the reason I didn't use this initially is the server for this is kind of flaky. But okay, so this seems to have gotten us something, right? So if we plot this new one. So this is precipitation in July, right? And so you can see that, for example, the east coast of India has a lot of precipitation, the west coast of India has a lot of precipitation, a bunch in sort of sub-Saharan Africa, North and South America as well. And so now, again, this gives me a different value. But it's not just that you can access the raster with single values. I have a data set of all the countries in the world. Let me get the precipitation that fell in those countries for this month. And the way I do that is I say rasters.zonal. So the first thing I do is I pass the reduction function. So what do I want to calculate? In this case, I want to get the sum, right? So the total precipitation. So I get the sum. I pass in the raster as my data. And I say I want it to be with respect to these polygons, right? Countries.geometry. Okay, so let's run this. And there you go. So I can probably also plot this thing, right? So plot, let's see, precip. So I can get this sort of list of precipitation. I can plot this and say that the color should be precips. Oh, what happened there? Ah, okay, I guess. Huh. Ah, it's a union of missing. Okay, okay. So here, of course, because there is missing data here, raster, the sum function added missing to an integer value, so that became 0. But we can also say skip missing equals true. Oh boy. Really? Huh. Strange. Yeah, not sure what I'm doing wrong there. This is the danger of live coding, I suppose. Although there is a tutorial on the rasters docs that I wrote about this, so it really should be fine. Anyway, okay, so there's this tutorial here that I can just walk through. So they got the same raster in this tutorial, right? And looking at just one country, in this case Chile. And let's suppose initially that you just get, so if you just got the mean or the sum of all of the precipitation values here, that would actually be wrong, right? Because your cells have different latitudes, and they have different areas with the different latitudes as you go further south or further north, right, from the equator. And so what you can do is you can actually, raster has a function that allows you to compute the cell area, and you can then weight each precipitation number by its area, and then sort of get a true average precipitation. And so in this case, when we accounted for the cell area, and that was literally just done by taking the raster of the precipitation, multiplying it by a raster where each cell is the area of that cell, the value of each cell is the area of that cell, right? And then when you compute that, you get about 110 millimeters of rain per square meter. According to the internet, it's supposed to get about 100 millimeters of rain per square meter in June, so that seems pretty accurate. If you don't account for cell area, what ends up happening is that you over-bias towards the poles and under-bias towards the equator, right, in sort of statistical terms, and then you get a value of 118. So there's a lot of, the big idea about all of this stuff is that it's very flexible, right? You can sort of pick and choose small building blocks and then do what you want going ahead of that. So I do have a couple of cool demos. Last couple of years, last like 6 or so, or 8 or so months, I've been doing a bunch of work with satellite visualizations. And so this is one thing from Geomarchy, where we've actually got data from this morning from a EUMETSAT satellite that, wait, Simon, do you work on this team? Yeah. Okay, yeah. So Simon works on the team for the satellite. And this is basically capturing wind direction and velocity, right?
I work on the instrument.
Ah, okay, yeah. So this is capturing wind direction and velocity both, right, I think? Yeah, I'm pretty sure. Yeah, so you can see that I think this doesn't quite get the island, but it gets kind of close. So this only captures over the ocean, but this is actually showing the satellite in orbit, which is this sort of blue dot with the yellow line indicating the orbital line. And then as I move this play bar back and forth, you can actually get, it incrementally will populate the swath of what the satellite is seeing. And there's also a little play button, so it can keep going and so forth. But yeah, so this is all built off of Geomarchy's new globe axis feature, which is basically just, you plot as usual, but it gets projected onto a three-dimensional globe instead of some two-dimensional surface. Another cool thing that we did, and this was I work with JuliaHub, and we have a modeling and simulation product called Dyad. And so this is a simulation, or a plot of a simulation of a satellite that's orbiting the Earth. And it's got, if you look down here, it's a bit small, but you can basically see that we're simulating the power system of the satellite. The little yellow line that comes out is actually when the satellite is in view of the sun, right? And so that's when it's getting power. And you can see that this trace down here is actually the power that's stored in the battery. And so whenever this light turns red, you're out of the sun, right? And you can see that then the battery starts to drain. Whenever you're in green, then the battery starts to charge again up to some threshold. Over here, this is one globe axis, right? I'm keeping the camera fixed. This down here is another globe axis where the camera is in the same position the satellite would be and oriented in the direction that the satellite is traveling. So you basically see what the satellite would have seen. Then this is a regular geo axis from Geomarchy, right, which is sort of just a projection. And I'm not sure what happened to my zoom. Probably need to fix that somehow. But yeah, this is completely interactive, right? You can scroll around, you can play, you can pause, all of that fun stuff. So let me see, I think, yeah. Oh yeah, the other cool thing I wanted to show, and this is probably one of the last cool things. So same time last year, Milan, Simone, and I were talking about taking data from one kind of grid, let's say a latitude-longitude grid, and projecting it onto, and sort of regridding it onto a different kind of grid, which might be a heel pix like Milan showed or something else. And so their use case was for basically an operator as a sparse matrix that can switch between the grids. Felix and a couple of people from his group had a different use case, which was that, so the data here is relatively small, right, in terms of big data. Felix's group had a different use case where they had huge data, which they wanted to regrid from latitude, longitude to some distributed global grid system. But in that case, I think they wanted to do analysis. And so what I'm showing right now on this globe is the latitude, longitude data set, right? And so you can see that this is pretty regular. These are these pretty regular sort of rectangles, right? They're all oriented, all the sides are oriented in the north-south or east-west directions. But we reprojected this actually on the fly to, in this case, this is, I think, the IC20 projection, right, Felix? Yeah, that's the usual one, right? Yeah. So this is a projection which, if I zoom out a little bit here, yeah, you can probably see these very, very faint triangle-like things as I'm scrolling around. And so those are actually the points where the grid changes direction. And so the idea with this grid, and I'm sort of zooming in on this just to show that, the idea with this grid is that all your cells are approximately equal area and have only 4 neighbors. In this case, I think, yeah, it's only 4 neighbors that share a side, right? So you get a bit semantic there. But the code to do this is actually, like most things, the user interface still needs a little bit of work, but it's actually not that bad. And this is, I don't know if we published the package, but if we haven't, then we probably will soon. So I get the raster, and I basically said that, I basically said that I want to simulate as if this raster, as if it had 75 by 75 chunks, right? So you could imagine that there was a collection of files and each had a 75 by 75 pixel portion of this larger raster. Then I say, okay, this is a latitude longitude grid, and I want to project this onto this IC grid. And so the way that this other approach works is it actually first tries to compute which chunks of the source grid are connected to which chunks of the destination grid. And so that's really more optimized for this kind of big data use case, as opposed to the simulation use case where you're not really super worried about chunking necessarily. But yeah, then all you really have to do is you say, okay, here's my source, here's my target, right? And I want to create a lazily projected disk array. And so this thing is, right now, no computation has happened. And then if I index into it, all of a sudden it will go in, it will find the correct chunks from the source grid, it will reproject them onto the target grid. At this point, it's just nearest neighbor interpolation. And then I can materialize the entire array. It doesn't take super long. And yeah, so I can plot that, and that's the plot that you saw on the full screen. The plot takes much, much longer than the actual reprojection because it has to instantiate every single polygon, which is also something you can kind of compensate for with some clever graphics, but not too much. Ah, okay, that was this one. Right. So yeah, you can see that I think there's another point somewhere in Africa where the grid changes, which is always cool to show, but I can't. Ah, there it is. Yeah, so you can see that there's another point where the way this grid works is that it splits the globe up into 20 different planes. And those planes usually look like triangles on the sphere. And so you can see this is one point where 3 of these planes kind of intersect. And so that, oh boy, that's sort of in this area, right, where you can see the pretty clear discontinuity in the direction of each of these grid cells. But yeah, so I think that's sort of most of what we've been up to. It's very cool stuff in geometry ops, regridding. Lots of cool stuff in rasters.jl that I didn't cover. But yeah, if you want to talk about that, Felix or I can probably speak to that. Bunch of ecosystem integration stuff. And yeah, thanks everyone. See you next year, hopefully. All right. Any questions?
Yeah, I don't think you talked much about Tyler. Tyler is this thing that I got really excited to when 2 years ago it got created, and then last year I got sort of demoralized with the sense that it was not working anymore. So do you want to sort of?
Yeah. So Tyler is an interesting situation. So right now, Tyler works for the very specific use case where you have data in either WebMercator or latitude longitude, and you want to plot that. And so right now, Tyler, you can plot a Tyler map onto geomarquee geoaxis. You can plot it onto a regular axis. The thing that we have not done, and it's mostly because we haven't had time to do it, is that right now, the tiling scheme of Tyler is fixed. Right? So it only really understands this very specific sort of web map tile scheme. Which means that your bounding box has to go from negative 180 to 180 and negative 90 to 90, right? That was something that I was hoping to fix this week. We'll see if there's enough time to get to that, but if not, then I do want to fix that soon enough, yeah. And so once that is fixed, then I think Tyler will be much easier to use for a variety of cases. But it does broadly work right now.
By the way, Tyler you weren't here, but
yeah, I think this was, yeah.
Raphael, Charlton, and Martin, and Gael, and Felix created that here in JuliaEO 23.
Ah, so this is the perfect place to do the refactor, right?
Well, thank you very much. Thank you, Anshul. Thank you, everyone, for a day full of new information. Very interesting presentations. We're going to stay in the room for the expert hour, or nearly. We're a bit late. So if you are online, the day ends here. Thank you for being with us, and we'll see you tomorrow at 9 o'clock again.